Washington, actually the basement studios. We're going to try to do this live and see how it works this time. I have another alternative. One of my daughters is a professor of medicine at Michigan, and one of her colleagues came up with a interesting way of trying to lecture during a pandemic, and I may try that next as well, but we'll see whether and if this works. So today I'm going to finish up a bit about how you estimate things, that is numerical optimization. Then I'm going to talk a bit, just a tiny bit, about testing, because some of you have to do some testing. You're writing your senior theses. Then I'm going to talk about so-called Bayes boundaries. And you'll see where that's heading eventually. We've already done a little bit of that. We're going to do some more of that. Then as another method of estimation besides logistic regression, I'm going to do a non-iterative method called linear discriminant analysis. Linear discriminant analysis sometimes does a better job than logistic regression, but only under some really strong assumptions. The logistic regression that we've talked about is really good only for binary choices, a 0-1 choice. You work, you don't work. The linear discriminant analysis is good for multi-class problems. What do I mean by a multi-class problem? You didn't go to school, you went to a 4-year college. With a 4-year college, you went to a state college, you went to a private college, you went to an international college, and you could even specify the colleges. And you pick one of those, and you do it. Okay, that's a multi-class problem. And the book, the ISLR, kind of waves its hands and says, well, that's too hard for you all. It really isn't. And I will give you a somewhat non-standard way of discussing it. The key thing going forward now, when I specify these models, is not going to be, oh my gosh, how do we estimate that thing? It's going to be, oh, I'm going to do maximum likelihood, at least for a while. And I'll just tell the computer, here's my model. Here's the maximum likelihood I want you to do, and it will go and do it. And if it fails on you, you'll know where to look. So today, to start with, I'm going to talk about another method of optimization. It's called coordinate-wise optimization. Now recall, we have a beta. It's what we want to estimate. We have an L beta, that's the log likelihood. And what we're going to do is do hill climbing. What do I mean by that? It means that I'm going to pick a direction and I'm going to walk up in that direction. Okay? And so what we're going to start with is we have a beta 0, which might be, I'll do it in case of 2, beta 1, 0, beta 2, 0, as a starting value. That is, a starting value for the first component of B, a starting value for the second component of B. Quite often, the default is 0. Problem with that. Sometimes 0 won't make any sense. Sometimes you can't do it. For example, if it turns out your model's quite complicated and a beta of 0 in there would have something that had the logarithm of something that is now turned either 0 or negative. So sometimes you will have to choose things other than the default. So even though you might want to start with the default, it isn't necessarily the case you should do that. Okay? So, and then our algorithm is that beta t equals beta t minus 1 plus alpha t, a scalar, times dt. Okay? So this is the current value of our estimate. Alpha t is the step size, and dt is the direction we're going. Okay? And these iterative models like this are characterized in large part by d. That is the direction you go. Now, in all of these, we're starting at some point and we're saying, we're going to go up somehow defined. Okay? And so last time we talked about dt equaled the gradient of L evaluated at beta t minus 1. Okay? So this gives you gradient search. You go in the direction of the gradient. The gradient is the thing that's taking you up the fastest at this point, beta t minus 1. Another thing we could look at, so this is called gradient, Sn. And if you want to descend, you just take the negative of the objective function L. Another d you could do is of the form h dl d beta t minus 1. Okay, and let's say that we have p parameters we're estimating. Then the gradient is going to be a p by 1 vector, and this h is going to be a p by p matrix. If you take it to be the identity matrix, you get gradient descent. Okay? These are called quasi-Newton or gradient methods. Notice the S on there, gradient methods, because there's more than one of them. If it's the case that h, which is p by p, is equal to minus the matrix of second partial derivatives, and you don't need to worry about this, just inverse, then the method is called Newton-Raphson. Okay. Now, if you're close to the optimum, Newton-Raphson, I misspelled that, this is SON. If you're close to the minimum or maximum, Newton-Raphson will converge pretty quickly and pretty accurately. If you're far away, gradient descent can work quite well. And the quasi-Newton methods oftentimes move by changing h from gradient descent to Newton-Raphson. Okay? So, by and large, you're going to use some variant of quasi-Newton. And so, in addition to telling the computer what the starting value is, what your line search is going to be, the direction is going to involve a gradient and a weighting matrix. And you'll have to tell it what that weighting matrix is. Typically, it's going to be the Broyden, Fletcher, Goldfarb, and Shano method. Or you can use Newton-Raphson. Quite often, when you get stuck, the thing to do is stop. Okay. Take the current beta that you have, restart the process with that beta as the new starting value, and pick another different method than what you were using. And you just kind of do that until you converge. Okay? So these are the gradient methods. And when they work pretty well, but they don't always work. And so what I'm going to talk about today, briefly, is one that we're going to use throughout the quarter. It's what GLM and GLMNet use, unless you get into the guts and change it. And it's called Coordinatewise Optimization. By the way, if I need to write bigger, just send a note to Herbert and I will try to write bigger. I know the lighting here isn't as good as I would like, but trying to find something that works. Okay, so I'm going to draw a picture here to illustrate coordinate ascent. And basically what we're going to do is we're going to move in a direction parallel to one of the coordinates. And we're going to move in the up direction. So this be beta 1. This be beta 2. And let's say these are the level curves. Of the function that I'm trying to optimize. So these are the level curves of the log likelihood, and it moves up this way. So this is a mountain sticking out at me. Now, what's the first thing we have to do? We have to pick a starting value. So I'm just going to pick one right here. And so this is going to be beta 1, 0. This is beta 2, 0. And that point is beta 0 with components beta 1, 0 and beta 2, 0. And now what I'm going to do is I'm going to move in a direction up. Well, if I start here and I move parallel to the beta 1 axis, I don't go up. So I'm not going to do that. Let's say that I move parallel to the beta 2 axis. Well, you can see what happens. I go up, 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 up. I hit this, I'm still going up, 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 up. And somewhere in here, I run into another level curve. And if I keep going, I'm going down. So up, 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 hit that point, down, down, down. So I want to stop there. Okay? And so this is going to be beta 2, 1. And beta 2, 0 is going to stay beta 1, 1 is going to stay beta 1, 0, because I don't change that. Okay. Well, now I pick the other axes and I move again. And again, I'm going to run into a level curve and start going down. Okay. So what happens here is I get beta 1, 2. I've already taken the first iteration. And beta 2, 2 stays beta 2, 1 because I'm not varying that. Okay? So I have now a beta 0, a beta 1, and a beta 2. I now go up this way. I run into, and note, it's a tangency where I hit those things, where I start going down. And so I go up at 2, and I get beta 2, 3 right here. I do it again. And maybe I hit something here. And then I do it again. And maybe I hit something here and there, and I hit it. And so you see how I collapse in on the optimum by moving in an up direction parallel to the axes. Now, this can take an awful long time. And coordinate-wise descent can be very slow. That said, if your underlying function is, in this case, we're maximizing concave, or if you're minimizing convex, so there's these nice level curves, it will be the case that coordinate-wise ascent or descent will always work. And that's why we tend to use it. So, in particular, any questions about this before I erase it? Okay. So we have beta t equals beta t minus 1 plus alpha t plus dt. Alpha t is the step size, and that step size can be negative. That is, you can go backwards in the backwards direction. I do that so that this dt can always be a gradient. And for coordinate-wise, dt looks something like this. The first one will be 1, 0, 0, 0, 0. Okay, this might be 1, and then d2 might be 0, 1, 0, 0, 0, and so on. And the key thing here is that the directions will be a vector of all zeros and a single 1, The 1 will be in the place of whichever axes you're going on. And these are the classic basis functions for, in this case, 1, 2, 3, 4, 5, Euclidean 5 space. So only one, all the rest zeros, and that specifies the direction you're going into. And then sometimes you'll want to go one way, sometimes you'll want to go the other way to be going up. Remember, you always want to go in the up direction. Simply moving along parallel to an axis won't do it, because it may be you're moving parallel to the axis and going back the other way. So just look at that picture I just drew. So coordinate ascent is by and large what we're going to use. It's quite robust. It won't break down on you a lot. When you get into commercial situations, you'll want to know at least about the other methods, and then you can sit down and read a book about them. There are whole books written about every single one of those. You can find the discussion of all the things I mentioned there in Wikipedia. And just a small point about Wikipedia, the German Wikipedia on science stuff is much more accurate than the English one for reasons nobody can explain. Well, my German friends all have an explanation, but you can imagine what theirs is. So, your job when you're working with data is to understand the background of these models a little bit. But your key job is going to be to formulate the likelihood. And as the course moves on, we'll spend more time in talking about how do you formulate a likelihood and how do you make the likelihood, the maximum likelihood, tell you a story about the data. The hardest thing about empirical work is not this. The hardest thing about empirical work is setting up the model in the first place, and then when the results come out, interpret the results so that, as somebody says, the results sing, and everybody goes, oh, I see, I see. So we will talk about that as we go a little further. Now, a little bit of a digression here. I will come back to this later in the quarter, but for people who are writing their theses, I just wanted to mention, okay? Testing. Hypotheses. So with likelihood, the hypotheses to be tested are typically linear hypotheses. So for example, the null hypothesis, beta 1 equals 0. The alternative hypothesis, beta 1 is not equal to 0. And we could have one-tailed tests, but I'm not going to lecture about that much. If you remember your 482, everything they said there is pretty much the same as we'll talk about here, except how you get the test statistic will be different. More generally, we'll have something of the form R, which is an S by P matrix, beta, which is the P by 1 vector, equals little r, which is S by 1. And typically we will have S less than P. If we have S equal to P and R is full rank, then that we just solve for beta there, there's nothing to estimate. And the alternative hypothesis is, in fact, I'm going to write it this way now. It's going to be not H0. Okay. Now, there are other kinds of hypotheses, but for right now, these are the ones we're going to worry about. And I'm going to write down some hypotheses. Keep track of this. I have to erase this now. I'd like to keep it on the side of the board, but I don't have any room for it. And I'm going to give you some examples of these so that you say, oh, I see just about everything I could ever specify as a hypothesis can be written in this form. And then most of the computer programs, when you try to do testing, they'll ask you for R and they'll ask you for little r. They'll ask you for big R and for little r. So let me give you some examples.
Wait, I have a quick question.
Yes.
What is the subscript to those? It's kind of hard to see. It's a little fuzzy. Is it S by P? And then what are the other ones?
So this is S by P. This is P by 1. And this is S by 1. So we have S restrictions. We have P parameters. And I'm going to give you some examples. And you'll see how these come out. I'll write this out again.
Okay, thank you.
Let me ask a question. Is anyone watching this on a large screen TV or a larger than your computer monitor?
I am
Yes,
just
I am.
on my computer.
You're doing it on your computer? Is somebody looking at it on a larger screen?
I have it connected to my TV. It's a 40-inch, I think.
Okay, and does it come through clear on the 40-inch?
It's slightly fuzzy, but it's definitely readable.
Okay. I was hoping that, but I couldn't be sure. So let's consider a hypothesis of this form. Beta 1 equals 0 versus the hypothesis beta 1 is not equal to 0. And the way I'm going to rewrite this is the following. I'm going to say this is 1 times beta 1 plus 0 times beta 2 plus ... plus 0 times beta p equals 0. Would you all agree with that? And if that's the case, then I have R is equal to 1, 0, 0, 0, 0, 0. I have little r equals 0. Okay? And in this case, this r is a p, pardon me. It's 1 by p. That is, it has 1 row in p columns. And R is 1 by 1. So this is a situation where there's just one restriction. Let's take something a little more complicated. Let's take the null hypothesis, beta 1 plus beta 2 equals 0, and beta 3 is equal to 3. Okay? And the alternative hypothesis is not H0. So this is a joint hypothesis, and you have to do a joint hypothesis test. So with the regression model, you would do this with an F-test. Okay, well, let's write it in the form that I mentioned. Okay, so this is going to be 1 times beta 1 plus 1 times beta 2 plus ... 0 times beta 3 plus ... plus 0 beta p. And that's the first restriction. And we have that equaling 0. So I'll put 0 here. And then I have 3 equals 0 times beta 1 plus 0 times beta 2 plus 0 times beta, 1 times beta 3 plus 0 times beta 4 plus ... 0 beta p. And so I can rewrite that in the form 1 1 0 0 0 0 0 0 1 0 0 0 beta 1 beta 2 beta 3 ... Okay, and that equals what? It equals the vector 0 3. And so this is big R, and that is 2 by p. And this is little r, and this is 2 by 1. And this is our beta, which is p by 1. Okay. So when you have many hypotheses to test, you cannot test them one by one. You can't do a t-test for one, and then a t-test for another, and a t-test for another, and a t-test for another, and end up with a sensible answer. Why is that? Well, let's say you do all your tests at the 5% level, okay? And so that says, under the null hypothesis, there's a, if the null hypothesis is true, there's a 5% chance I'll make a mistake, just by random. Now, let's say you do 1,000 t-tests on one regression. The probability you will make at least one type 1 error is 100%. Okay? On the other hand, that really isn't what you want to know. Okay? And that will lead us later on to a discussion of false discovery rate analysis and some ways of avoiding having to do certain kinds of tests. Okay. Now, most programs you're ever going to run into are going to have a test method. So you'll do an optimization, you'll get your results. You'll have a predict method. So you'll take those results and you'll do a prediction, and maybe you'll give it a set of new variables and say predict for those new variables. It will also have a test method. And I don't mean test in the sense of a test set, but test in the sense of a hypothesis test. And you can do basically 3 kinds of tests with likelihoods. And those are the only ones I'm going to talk about here. So you're going to write your hypotheses in terms of these linear hypotheses. And then you choose from 3 types of tests. And these tests are essentially equivalent. That is, the p-values you get from them tend to be roughly the same. Not identical, but close enough that you really shouldn't have to worry too much about choosing between any of them. The first one is called the likelihood ratio test. Okay. And what the likelihood ratio test does is it estimates log likelihood under the null And let's call that L hat 0. It also estimates log likelihood under the alternative, and let's call that L hat 1. And then the test statistic compares L hat 0 and L hat 1. And in fact, the test statistic's pretty simple. It is L.
On the board, on the right top corner, I think there's like a little bit of reflection on there, so we cannot really see clearly.
Up here?
Yeah.
Okay.
Sorry.
No. Look, we're inventing this stuff as we go along. So estimates the log likelihood under the null. Can you see that?
Yeah, thank you.
Okay. I'll try to stay away from that corner of the board. So the statistic is L 2 times the number of observations you have, the log likelihood under the null minus the log likelihood under the alternative. And it turns out that this is going to have a chi-square distribution with degrees of freedom equal to the number of restrictions, basically that S in the function. Now, you don't need to worry about this, because what you're going to do is you're going to say do log likelihood, and then the computer's going to give you back a p-value. Okay? And what you're going to do is you're going to reject if that p-value is too small. Okay? So if that p-value is too small, it says this is a ridiculously unlikely event if the null hypothesis is true. So if the null hypothesis is true, you would get this less than 1,000th of the time. And so you say, yes, I know it's possible that can happen, but rather than believe I got hit by that extraordinary rare event, I'm going to believe that the hypothesis was wrong. Okay? So you say, computer, do a likelihood ratio test. And the computer says working, and then the computer spits out p equals 0.6. And you say, well, 0.6 is pretty high. That's easily likely under the null hypothesis. It happens more than half the time. So I can't reject the null hypothesis. This just isn't unlikely. If I believe the null hypothesis in the first place, which you better because it's your null hypothesis, then I'm just stuck with it. On the other hand, if it says p is equal to 0.006, you say, 6,000ths of a chance, man, that's really small. Rather than believe that unlikely event happened to me, I'm going to assume that the null hypothesis is incorrect. Because remember, these p-values answer the question, how likely is this if the null hypothesis is true? Just remind you from basic statistics, when you're doing this, you have to decide in advance what the threshold is going to be. So you haven't done any estimation, you haven't done any testing, you're getting the data set up, and you and whoever you're arguing with are going to do what? You're going to agree on a threshold p-value. Okay, so if your p-value is less than 0.05, then you're going to reject the null as being just too unlikely. Why 5%? Well, you should play around with what 5% means. 5% is pretty unlikely. I don't know if you did that in 482, but we really don't have the time to do it in here. But you should try developing some card tests to see how unlikely a 5% event is. So this is the first method. Now, what's its drawback? Its drawback is you have to do 2 estimations. Typically, you will do the restricted estimate first. That is, estimate the log likelihood assuming the alternative hypothesis. And then you will take the parameters you got from that and use them as starting parameters for the nonlinear maximum likelihood estimation for the unrestricted likelihood. However, sometimes you will find that you can't get the unrestricted likelihood. It just won't converge. Other times you'll find you can't get the you can't get the unrestricted likelihood because it just doesn't converge. Other times you won't be able to get the restricted likelihood because it won't converge. And so there are 2 other tests you can use, and we'll talk about those next. And most modern computer programs that cater to econometricians have all 3 of these tests. So the second test is the walled test. Okay, and it's based on the asymptotic distribution of the unrestricted maximum likelihood. Okay, and I won't go into what the test looks like. If anybody wants me to, I can write a little note on it. You can go to most econometrics texts and look up the wall test. The key thing about the wall test is that all you have to do is estimate the likelihood function under the null. Okay. The disadvantage of it is that it's based on the asymptotic distribution of the likelihood estimates, which involves estimating a variance-covariance matrix. And it turns out that variance-covariance matrix can be quite inaccurate. So what we know about the likelihood ratio test is all we need are the optimands. All we need are the maximum likelihood under the null, the maximum likelihood under the alternative, and we don't have to estimate variances, and it's cleaner in that regard, but you do have to do twice as much work. The third test is called the Lagrange multiplier test, or the score test. It's called an LM test, sometimes called the Rao score test, and sometimes simply called the score test. Okay, and it's based on the restricted estimates. So you have a bunch of restrictions, and for those of you who've done some Lagrangian multipliers, if the restrictions don't hold, then the Lagrangian multipliers are 0, and so it's a test for whether certain Lagrangian multipliers are 0. But again, you don't have to know that. What you need to know is, look, I need to get one of these tests done. You try and do each one of them, and they're going to give you p-values. Okay? If they all give you p-values that are about the same, you're home free. More often than not, when they don't give you p-values that are the same, it's because one or the other has failed. You haven't been able to get a restricted estimate. You haven't been able to get an unrestricted estimate. And so whichever one you use, you're going to get a p-value if it succeeds. And then you're going to reject the null if that p-value is too small. And it's as simple as that. So you set up your test. You don't have to worry about the structure of the test. You don't have to look up tables. You don't have to do anything like that. It's going to sit there and do all of that for you, and it's going to say the p-value for this test is 0.004. Was that too small? And you will have decided with whoever you're arguing with whether that's too small or not in advance. Okay? And that's all I'm going to say about testing for the time being. I'll come back to this when we talk about false discovery rate control and model selection. So I don't want to say much more about estimation. When we talk about things like the LASSO, when we talk about backpropagation, when we talk about most of those things, I'll simply say, oh, and this algorithm they're using here is coordinate-wise, or this algorithm they're using here is typically Newton-Raphson, or it's some gradient method. Or when we get to neural networks, I'll say, it turns out these methods don't work, but for a reason you might not expect. One is you don't have convexity, which causes a whole lot of problems. The second is oftentimes you have too much data, and there's no way you could actually kind of, in any sensible fashion, handle all the data for each iteration. And when we get to that point, we'll talk about stochastic gradient descent. But as you will see, it's just a sensible variant of what we've talked about so far. So, moving away from that, I want to go back to talking about a logistic regression. And I want to talk about the Bayes boundary. And we looked at that a little earlier. I want to talk about it again. So recall y hat equals 1 if p hat of x is greater than 0.5 and equals 0 if p hat of x is less than or equal to 0.5. What do I mean by that? You give me an x, and I will classify the person who has that x of either being in class 1 or class 0, depending upon which is the most likely class. Okay? So you give me your x's, I plug it into my COVID model, and it says the probability that you've had COVID is 0.99. I'm going to say, I'm going to classify you as having had COVID. In contrast, if this probability comes up 0.01, I'm going to say, it's unlikely you've had COVID. The problem is going to be in the middle, and we're going to see that this is going to arise not in the, maybe the next lecture, but the lecture after that probably, is where P is 0.51 and 1 minus P is 0.49, and it's kind of like, well, maybe she had COVID, maybe she didn't have COVID. That's where you're going to start getting your false positives and your false negatives, which for COVID might be quite bad. So I say, you've had COVID, you can go back to work. You're safe. You go back to work with all those people who had COVID before, and maybe they had some in their clothes, and all of a sudden you're down with it because there was a false positive. It said you had it and you were immune when you weren't. And that usually happens for those things right about the cutoff. Well, we're going to start talking about that cutoff. Okay. This is nice and intuitive, but I'm going to do it a little bit differently than this. Okay. I'm going to note the following. I'm going to note that P hat of X being greater than 0.5 implies that P hat X over 1 minus P hat X is greater than 1. And I'm going to derive that for you so you can see how it's derived. It's really pretty simple. Okay. But can any of you see where I'm heading with this? Logistic transformation. I'm going to use the logistic transformation on this, and I'm going to come up with a really pretty picture that will give you a good deal of insight into how these classification methods work. So I have to erase this. And I'm going to rewrite this up here. So I'm going to say P hat X over 1 minus P hat X. Okay. And because I'm assuming that P hat X is greater than 0.5, it must be the case that P hat X is 0.5 plus some epsilon. This epsilon can be anywhere from 0 to 0.5, right? Those will all be greater than. And then this is 1 minus 0.5 minus epsilon. I'm just plugging in here. And what is this? This is 0.5 plus epsilon over 0.5 minus epsilon. And I'm going to bore you a little bit more. That's right, don't write in that corner, Greg. Can I erase this?
Yeah.
Okay.
Yes.
So let's look at that, okay? And I'm going to write that as 0.5 minus epsilon plus epsilon plus epsilon. Okay? That's a 0. So it's 0.5 plus 0 plus epsilon over 0.5 minus epsilon. Well, then I can rewrite this as 0.5 minus epsilon plus 2 epsilon over 0.5 minus epsilon. Do you all see that? And that equals 1 plus 2 epsilon over 0.5 minus epsilon. 1 is positive. 2 epsilon is positive. 0.5 minus epsilon is positive. So this is necessarily greater than 0. Okay? So if P is greater than 0.5, then P over 1 minus P, whoops, is greater than 1. It's certainly greater than 0, but it's greater than 1. Okay? So what are we going to do with that? Well, I'm going to rewrite this. My daughter, who's teaching at the University of Michigan, she looked at my lecture on this last night. I looked at hers on what she was doing, and she said that my whiteboard doesn't erase very well, and it leaves streaks, and I should erase it more often. So I'm going to do that. Okay. So where were we? We had P hat X over 1 minus P hat X is greater than 1 if P hat X is greater than 0.5. And in fact, this is an if and only if statement. Okay? So what this says is, if your characteristics are given by the vector x, and P of x is greater than 0.5, then I classify you as y equals 1 if P hat is greater than 0.5. Alternatively, I can classify you as 1 if P hat over 1 minus P hat is greater than 1. Okay? Now, let me take the logs of that. So this is log P hat X over 1 minus P hat X is greater than 0. Okay? So I will classify you as y equals 1 because P hat X is greater than 0.5. I will also do it, and it will be exactly the same result if the log odds for x are greater than or equal to 0. So I can calculate the log odds, see if that's greater than or equal to 0. I can calculate P hat, see if that's greater than or equal to greater than or less than 0.5. And classifying you into y equals 1 here and y equals 1 here will always happen at the same time. You won't get any different result. So why would I want to do this? You might say, well, look, you've already got the probability. Why do you divide by the log? Why do you divide by 1 minus the probability and take the log? That just seems like a lot of wasted effort. And here's the reason. Recall that log P hat X over 1 minus P hat X is equal to X beta hat, where beta hat is the MLE for the logistic regression. Okay? So let's look at that carefully. The log odds are linear. And what this says is that if x beta hat is greater than 0, I classify you into a class 1. If x beta hat is less than 0, you're classified into the 0 group. And once I have beta hat, it is much easier to calculate x beta. Actually, this probably should be an x transpose beta. So this is 1 by p, and this is p by 1. So they're both p vectors. This is very easy to calculate. So you don't worry about the fact that this is true, that the log odds require some work, because they really don't. This is because of the logistic assumption. If we had some other kind of model, so later on we'll see a probit model. The probit model, this won't happen this way. So let's go a step further now. Going to see another picture. And here I have x1 and x2. So this is the first component of your vector that describes you or whatever situation you're trying to describe. And this is the second one. Okay? And here I have beta 0 plus, and I'll put a hat on there, beta 1 x1 plus beta 2 hat x2 equals 0. I realize I just wrote where I said I wasn't, so I'm going to do it here. Beta 0 hat plus beta 1 x1 plus beta 2 x2 hat hat, where the hats are the maximum likelihood estimators. So now we come in with an x, okay? Let's say that your x is right here. Okay, so this is x1u and x2u. Okay, this point is above or below this line. Well, it's above this line, so y hat u equals 1. Somebody else comes in. Maybe this is x1 me and x2 me. Right? And this is below the line, so y hat me equals 0. And it gives you a very nice way of visualizing the Bayes boundary. This is the Bayes boundary that separates those things that are going to be classified as 1 and those things are classified as 0. And I want you to note for right now that this is linear. However, I can change that. But we'll do that later on in the course. Now, there is something else that's quite important about this picture, and I'm going to redraw it. That doesn't look very good. Let's try this one. That's better. X1, X2. And now I'm not going to look at predictions. I instead am going to look at the data. And let's say my data looks like this. These are all the y's that are greater than, that are 1. And now I'm going to have all the data for the y's that are actually 0. So this is in my training set. Okay. And I want you to note something here. Let's see if I have a different color I can use. No. There is a line that goes through those 2 points, and it perfectly separates them. Here is another line that goes through those points and perfectly separates them. Here is another line that goes through those points and perfectly separates them. Any one of these lines could serve as the Bayes boundary. The problem is that this is equivalent to a problem like multicollinearity. That is, if you have perfect separation between classes, meaning that you can run more than one line and separate them, the logistic regression will fail. It will say, you have perfect separation between classes, I can't do this. By the way, it will also say that if there's multicollinearity. So in the regression case, if you have multicollinearity, you can't get an estimation. In the generalized linear model, in this case, the logistic regression, the same thing's true. If you have multicollinearity, you can't get an estimate. However, with logistic model, there's an additional problem, and that's if you have perfect separation between the classes, you won't be able to get a unique estimator. And we're going to handle that in 2 ways. I'm going to introduce you to a new, different classification method called linear discriminant analysis. Later on in the course, we will also look at support vector machines. And support vector machines are a way of handling this same problem. But for right now, I want to introduce you to linear discriminant analysis. Linear discriminant analysis came about long before the logistic regression model. And when the logistic regression model, was a physician named Berkson, came up with this, I think in the 30s. And people forgot about it for a while. And then it became very popular in the 70s. And all the statisticians jumped up and said, hey, wait a minute. You know, this is almost the same as linear discriminant analysis. And linear discriminant analysis never fails. It always works if the assumptions are there. And in fact, it's even better than logistic regression because you don't have to iterate. It's not a nonlinear method at all. It's linear. And so it's much easier. And so there was a big discussion for a while about which to use. Eventually, the computers got so good, it could do a logistic regression just like that. Logistic regressions take about 10 times longer than a corresponding regression. Okay, so takes 10 nanoseconds instead of a nanosecond. So logistic regressions go very, very quickly. So I'm presenting this in part because for historical reasons, in part because I want to introduce you to some Bayesian thinking, which you probably haven't done before. And thirdly, to give you a tool that you could use, although since R is free now, since R is free, when you go to whatever place you go to work, you could probably do a logistic regression. But, before the R package came out, that wasn't the case. You'd have to buy SAS, you'd have to buy Stata, you'd have to buy something. And the place you're working with might say, no, we don't want to do that. So I like it also because it's just kind of slick. And what you're going to see with it, again, is this linear boundary between classes. I'm going to do it initially in the case of 2 classes. I think the book does it for K classes and 1 variable. I'm going to do it for 2 classes and more than 1 variable. Okay. And so my assumption is we have Y and X. Okay. Y and X are jointly distributed. Okay. Y is our 0, 1 variable, and let's say X simply has 2 components. Let's say it's income and price of something. Okay. And this has a distribution, a joint distribution. I'll call it F of Y and X. But I'm going to have to really clarify this because Y is discrete and X might be continuous. X is almost certainly cardinal. Y is simply a label. So the way I'm going to do this is I'm going to make an assumption about the conditional distribution of X given Y. So F of X given Y, I'm going to assume is normal mu Y sigma squared. Okay. I hope you've all seen this notation before. Mu Y is the expected value of Y, expected value of X given Y, and sigma squared. In fact, I have to be careful here. Is a matrix. That is, I have the variance of X1, the variance of X2, and the covariance of X1 and X2. Okay. So mu Y, I'm going to say I'm going to write it this way. I'm going to have, it's the expected value of X given Y equals, and I'll put a 0 on here, Y0. And I have sigma I'll call it 0, 0. That's equal to the variance of x given y equals y0. And I have sigma 1, 1 equals the variance of x given y equals y1. And presumably y0 is 0 and y1 is 1, but it doesn't have to be. Remember, it's just a label. And finally, I have sigma 0, 1 equals sigma 1, 0 equals the covariance of x I didn't want to do this. I wanted to do it this way. Pardon me. That should be a 0. That should be a 0. Hang on. So I want. Okay, erase what I did there because I did this wrong. We're fixing y0, holding it constant. Okay, so let's redo this. Okay, this is correct. And then I have a variance 0, 1, 1, and that's going to be equal to the variance of x1 given y equals 0. That's what I want to do. Variance 0, 1, 2, and we won't call it that. I'll call it covariance. I'll just call it sigma. Okay, and this is going to be the covariance of x1 and x2, y equals y0. And finally, sigma 0, 2, 2 is going to be the variance of x2 given y equals 0. And now if you want to go to y equals 1, just replace that first 0 in there with 1s. Okay? The point is that if I have two classes, the x's for those classes are normally distributed. They're jointly normally distributed. That is the assumption. So let's see what that gives us. So we have the distribution of x given y is normal with some variance covariance matrix of the x's for that y. And that covariance I'm not going to allow to depend on y. So I'm going to assume the variances are the same. And then you say, well, look, that's all well and good, but that's not what we're interested in. What we're interested in is the probability y given x. Okay? How is the probability y given x related to this? How is it at all? Well, you may remember that I could write, let's see, I'm going to write f of y given, f of x given y times the probability of y. And what is that? That's going to be the density xy. That's essentially what this is. Okay? So I take conditional on y, fx, multiply it by the probability of y, and that is the joint probability density of y and x. Okay. Now, how do I get the conditional? Okay. Well, the way I get the conditional is I have to divide by the marginal distribution of x. How do I get the marginal distribution of x? Well, it's going to be fx given y, and I'll write it y equals 0, times probability y equals 0. I'm going to have to erase this. I don't have enough room. I'll go back and do it. So let's try this again. So I have the probability y given x equals the density f of x given y times, and I'll make it y equals 1. So this equals 1 times, and I'll just call it pi 1, the probability that y is equal to 1, divided by x given y equals 0 times pi 0 plus f x given y equals 1 pi 1. And from your basic probability and statistics course, you should recognize that as Bayes' rule. Okay? That is, I've converted a statement about f of x given y into a statement about y given x. Okay? So let's look at that. And we say, okay, we're going to assign x to y equals 1 if probability y equals 1 given x is greater than the probability y equals 0 given x. Okay? Because this would be greater than 0.5, and that's going to be greater than this. I'm going to move to a black pen. This isn't working as well as I would like. So let me go to the top here. I think I'm seeing how to do this. Rather than, so my usual way is to break the board up and go down the class like that. I think maybe what I have to do here is work down and then go to the top. And that way I'm not erasing things that I need. Okay. So I have P y equals 1 given x is greater than P y equals 0 given x. Okay. And the one thing I want you to note is both of these probabilities are going to have the same denominator. Okay? So I'll leave that there for a second. And so what this says is that I'm going to have f of x given y equals 1 times pi 1 greater than f of x given y equals 0 pi 0. And I'm just going to write denom. Okay. And since the denominator is the same for both of those, I don't need to calculate the denominator. Okay. So what that says is that the probability y equals 1 given x being greater than the probability of y equals 0 given x is the same statement as the conditional density of x given y equals 1 times the probability y equals 1 will be greater than f of x given y equals 0 times the probability that y equals 0. That's because those denominators cancel out. You're going to see a whole bunch of magic here. Okay. Let's assume that x is in R1. Okay. I won't work with the matrices, just illustrate this, and then I'll write the final answer down. Okay. If that's the case, what is f of x given y equals 1? Well, that's 1 over root 2 pi sigma squared exp to the minus x minus mu 1 over sigma squared 2. Okay? That is the density of a normal with mean mu 1 and variance sigma squared. What is f of x given y equals 0? Well, that's equal to 1 over root 2 pi sigma squared exp minus x minus mu 0 over sigma squared 2. Okay. Now, if you look at this condition here and look at these two formulas, one of the things you're going to see is this term, 1 over root 2 pi sigma, appears on both sides, and so I can cancel those out. So let's do that. I'll write it back up here. Okay. And so this is going to be 1 over square root 2 pi sigma squared exp minus x minus mu 1 squared over 2 sigma squared. Pi 1 is greater than 1 over root 2 pi sigma squared exp minus x minus mu 0 over sigma squared 2 squared times pi 0. And my point here is that those cancel out. And so what that says is that my condition becomes, I'll erase all this now. assign to class 1 if what? EXP minus x minus mu1 squared over 2 sigma squared times pi 1 is greater than EXP minus x minus mu0 over 2 sigma squared pi 0. Okay. Now, anytime you see EXPs and products, what should you think of doing? You should think of taking logarithms. So, neither of these can be negative or 0, and so we can take the logarithm. The logarithm is monotonically increasing, so when I take the log of both sides, the inequality stays the same. So what do I get here? I get minus x minus mu1 squared over 2 sigma squared plus log of pi 1 is greater than, minus x minus mu 0 squared 2 sigma squared plus log of pi 0. Okay? We can simplify this more. Part of this exercise is the following. At the beginning, we could have just said, okay, we use Bayes' rule, we have this complicated thing, and just let the computer do it. But what we're trying to do here is to make this as simple as we can so we can interpret it. So, let's do a little bit of expansion here. Minus x squared minus 2x mu1 plus mu1 squared plus, mu1 squared all over 2 sigma squared plus log pi 1 greater than, again, and I'm going to write it minus x squared plus 2x mu0 minus mu0 squared over 2 sigma squared plus log pi 0. So I skipped a step here. Now, this is kind of a bad thing to do. You should probably always do this and then take the extra step. I had an old probability friend who, when I was a baby statistician economist at the labs, I was doing something and he goes, "Oh, I missed that step." And this is a guy who, if they gave Nobel Prizes to probabilists, would have had one. His name was Julian Keelson. And I said, "Oh, it's just like," he goes, "Don't be a hero." He says, anytime you're a hero and skip a step, and then your theorem doesn't work out or your program doesn't run, I can guarantee you that point where you tried to be a hero is where your paper failed or your program failed. And he was really, really accurate about that. And he said, and you don't have to be a hero. We all know you're smart, so you don't have to prove you're smart. If you're really smart, you don't make mistakes. And you don't make mistakes by trying not to be a hero. And so, even though I did it here, I should not have. By the way, it's a very hard habit to break. So it's really good not to get a that habit, because after 50 years, I'm still making that mistake. I'm going to get rid of this. I'm going to get rid of this. And then I'm going to rewrite this, okay? And I'm going to write it as minus x squared over 2 sigma squared plus 2x mu 1 over 2 sigma squared minus mu 1 squared over 2 sigma squared plus log pi 1 greater than minus x, move back over here, minus x squared over 2 sigma squared plus 2x mu 0, 2 over sigma squared, minus mu 0 squared over 2 sigma 0, sigma squared, plus log pi 0. And now when you look at this again, you say, wow, there's some more simplification I can do. Okay. What is that simplification? Okay. Well, this is on one side of the inequality, this is on the other side of the inequality, so they cancel out. Okay. You'll note that here you have a common set of factors. The 2's cancel out, so we'll get rid of those. Okay. And then we have the rest of this. And now what I'm going to do is I'm going to combine terms. I'm going to say, this says that x mu 1 over 2, over sigma squared, this term, minus this term. I'm going to move it to the other side of the inequality. So that's x mu 0 over sigma squared minus mu 1 squared over 2 sigma squared plus mu 0 squared over 2 sigma squared is greater than log pi 0, which I'm going to leave here, minus, and I'm going to move this over, log pi 1. Okay. Let's go one step further. You realize that this is x times mu 1 minus mu 0 over sigma squared minus mu 1 squared over 2 sigma. In fact, I'm going to write it as mu 1 squared minus mu 0 squared all over 2 sigma squared is greater than log pi 0 minus log pi 1. Now, one of the things I want to point out to you is this function is linear in x. Let's simplify a little bit more. I'm going to define a new function for you. I'm going to define delta x. And do I want to do it that way? Yeah, I'm going to define delta ix equals x mu I over sigma squared minus mu I squared over 2 sigma squared plus log pi I. Okay. This is called the discriminant function. Okay. Assign x to I star if di of x, di star of x, is the largest discriminant function. Now, note down here, this is just the difference in discriminant functions, and we're asking whether they're greater than 0. Okay. Note also that this discriminant function is linear in x. Okay. So, if I knew what mu I was, if I knew what sigma squared was, if I knew what pi I was, I could just plug those things in there. You give me an x, I plug it into the discriminant function, and I plug it in for each possible outcome, and I say you get assigned to the one that has the largest discriminant function. That's what so-called LDA is. Okay. Well, we have all this stuff to estimate, and I'm going to tell you that it's really simple. So, what's mu I hat? Well, remember, we assumed that our training data were normally distributed. Mu hat I is the mean for the ith group. Okay? And so that's just going to be x bar I. That is, I'm going to take my x's, I'm going to calculate their averages for the ith group, and that's x bar I. What about sigma hat squared? Well, that's going to be the summation, let's say n equals 1 through n, x, and how should I do this? I guess I'll do it. I'll do x n because I just have 1x. And then what I'm going to do is I have to subtract off the mean here, okay? And so this is going to be minus x bar n I, okay, squared over n minus 1. So the difference here is this is not the average of all of the x's. This is the average of the x's that the group that n turns out to be in. Okay? So that's pretty easy to do too. You look in the book and see how that's done. The final thing, what is pi 1 hat? Well, this is the probability that in the pi hat is the probability that a person drawn at random would be in class 1. How do you estimate that? Well, you look at the number of people that are in 1 divided by the total number of people. That's just that proportion we keep seeing, okay? So that means that I have estimates of that of that, of that, of that, and of that for all the classes. I take my x, I evaluate the discriminant function for each of the classes, and I assign the person that has those x to the classes where the discriminant function is the largest. And note, we did none. We did no iterations here. It's completely linear. Kind of slick. The crucial assumption is that the x's are normal. Now, in the case in which you simply have one variable, you can always transform the variable so it's normal. That's an easy thing to do. When we talk about simulation, I'll show you how you do that because it's one of the fundamentals of that. However, when you have more than one variable, it can be hard, if not impossible, to meaningfully transform your x's to normality. And so if you can't do that, this may not work. Okay. This may not work. It turns out when the data aren't very normal, where your x's, maybe your x's are in two groups. Not very normal, you know, bimodal. Bimodal in 2 dimensions. Multimodal in 2 dimensions. Maybe it's like having 4 mountains at different places on the x1, x2 plane. However, when that normality assumption holds, this works just about as well as the logistic regression. Works just about as well as the logistic regression. And back in the old days, we used to use these methods to help us get starting values for a logistic regression. There are better ways of doing that. They're already programmed in. Okay, I think we're going to stop here. Oh, one last thing. One last thing I wanted to mention. It's going to be a recurring thing. So let's say I have an x1 here, an x2 here. And this is the line where delta 0x is equal to delta 1x. Okay? And 0 down here, 1 up here. There essentially is the Bayes boundary line again. Again, it's linear, and oftentimes this line will be the same for the logistic regression as for LDA. And that's what I have to say for tonight. What I'm going to come and talk about next time is so-called multi-class problems. It's something that the book gives short shrift to. The book says, oh, it's too hard for you guys. There's no way you can understand it. And LDA will handle that just fine. Well, it actually doesn't handle it just fine. And multi-class problems are the things we use all around Amazon all the time. It's what Google and Netflix and all those guys use all the time. We have things that are more advanced than that, and we use those all the time too. But if you are in a standard multi-class problem and you don't do what we're going to learn next time, which is called the multinomial logit, you could look at what we just learned about the logistic regression as the binomial logit. If you haven't done a multinomial logit, they'll say, well, why did you spend all of your time and effort and waste all those computer resources if you could have done something simple? And so that's one of the things that I'm going to start harping on is, even if you have a really cool technique and you want to show people how smart you are because you know it, and you write your paper that way, an experienced, a mature researcher will look at it and say, well, couldn't you have just done a 2-sample t-test? Couldn't you just run a linear regression and done this? Why did you have to do all this neural network stuff? Because we want to keep things very simple as we can. Use the simplest tool that will adequately handle the problem. Now, there are lots of things where simple tools won't handle problems, and we're going to run into lots of those. You're going to see them in this class. So that's it for tonight. I put a reading for next time in notes on the website, in the files. It's called Simple Multinomial Logit, and I will take you through it. Again, now, I'm not going to tell you how to estimate that. I'm going to lay out the model, and then I'm going to say, and now you're going to do maximum likelihood. You're going to go find a program that does that. It's called mlogit, and you're going to say, do the maximum likelihood. And then your problem is going to be setting up the problem in the first place, showing that, in fact, it is a multi-class problem, and then interpreting the results at the end. And we'll talk a fair amount about that. Okay, that's it for tonight. Well, are there any questions? I forgot to ask that. Well, if it's blind mode, I'll give you an example. So here's x1, here's x2. And here's our x data, and this is, let's say that this is x given y equals 1. And then maybe so maybe that's what the underlying scatter plot looks like. And so you've got a kind of something looking normal here, something looking normal here, maybe something normal here. This doesn't look normal at all. And there's no way you're going to find transformations of the x's and y's or combinations thereof to make the joint distribution look normal. And so if that happens, the assumptions of the LDA are violated. And in fact, in this particular case, the LDA will just do terrible. Whereas it doesn't bother logits at all, doesn't bother logistic regression at all. Other questions? Okay, let's all go home and eat. See you next time.